This week, we will start talking about numeration systems. We will start off with the two of the oldest ones, Egyptian and Babylonian mathematics. We will discuss some sources, the number systems themselves through the student presentations, and I will also give some highlights of the mathematical achievements of these two cultures. We will then talk about the Greek mathematics and its very different approach to the subject. So let's think about numeration systems as a whole. A numeration system is a way in which we represent numbers. So, for example, the one that we generally use every day is 1, 2, 3, 4, and so on, is a Hindu-Arabic system that we've inherited from the Hindu-Arabic culture. Now, the way that our system works affects how arithmetic in our system works. So, for example, if I were to write or to want to add 12 and 9, I have to think about what happens when I add it together and how that affects my outcome. See how I then had to increase the number in the tens position and essentially decrease the number in the ones position. The arithmetic is affected by the numeration system, but this relationship is bidirectional. The number system affects the arithmetic, and arithmetic works the way it does because of the number system. We will see how in different number systems, different arithmetical operations were easier or harder because of that. Overall, the system actually affects how mathematics developed as a tool. What kinds of things was it created to support? What kinds of things were made easier with the specific numeration system of choice? And what kinds of things were harder and therefore not necessarily essentially needed? We will study different systems for their historical importance. We will think once again about the time period and the culture that they originated from, but also we will see what were the advantages and disadvantages of each one together with the one that we currently use to understand their purposes and their goals. We will start with the most ancient system of all, the tally mark system. We've already seen this bone, and the tally mark system is really probably still the first system used by children all over the world. We will simply tally up some marks, and however many I have currently notched or placed in front of me, that is going to be the total number represented. So there are no symbols other than a tally mark. The system only has one symbol. And for example, there's no number for 5. The 5 is simply represented by 5 of the tally mark symbols. The system is additive. So this one tally mark plus this other one tally mark equals 2. And think about these questions. Are there any other additive number systems that you know that work like that? Our system is certainly not additive. If I write 2 and 3 next to each other, this does not represent 5. This rather represents 23. Are there other additive systems that are commonly used or that you know of? And in this particular case, what are some advantages and disadvantages of this system? It's easy to say that it's clunky and primitive, but it definitely has some advantages. So think about those and go to the Padlet tool to write down what it is that you can come up with. Next, let's talk about more, let's say, developed number systems. So before we think about numbers themselves, let's think about the region where they come from and why do they even come from that region? What was so special about Egypt and Babylonian Mesopotamia that has created, there was this great development in certain mathematical aspects. Egypt and Babylon are located in this, what is called Fertile Crescent, that is nestled between the Nile and the Euphrates. And really, early mathematics emerged where there was fertile soil. Rivers made it possible. You can see how all of the fertile soil here that is marked in green is of course situated around rivers. The Nile and the Euphrates would flood, they would deliver nutrients to the nearby soils that could therefore then be harvested and so on and so forth. People not only were able to farm in those lands, they also needed to keep track of the Nile flooding, which in turn made them look up at the sky and notice other things that caused the Nile flooding and to keep track of it with maybe tally marks or more sophisticated systems. But even to this day, with modern technologies, the river is by far the most livable area. So if we take a look at, for example, the modern Egypt, we can basically track where the river is by the density population of it. The people still live close to the river, even though the water can be delivered much further. Now, what did that mean for the ancient world? Agricultural abundance meant many resources, and so people didn't necessarily need to spend all of their time farming. They could spend time thinking about when to farm, or making farming more efficient, or thinking about when the next farming season will come, and so on. A society started developing, and a society without some kind of functioning justice system, in a sense, would constantly be plagued by disputes over land and taxes and inheritance and so on. So this is where the earliest mathematicians really began to shine. Mathematics is objective. Mathematics is not something one can really argue with because it is precise. If there is an inheritance to be divided and somebody comes to divide the inheritance and shows you their calculations, no one can argue with that. Mathematics takes precedence over any kind of emotional things that you can have over things like taxes and land and so on. The authority of mathematics is also important because whoever comes to divide the land has to have the authority to prove that they are in fact capable of doing so. The Sumerian word for justice is niksisa, which literally means straightness, equality. So this rod and ring symbol that is depicted on basically all of the ladies' justice Mesopotamian stelas is a coil of measuring string and a yardstick. The lady justice is a geometer. Geometry is not something that one could argue with. She's holding her land measuring tools that are the instruments of justice in ancient society. Now, this also comes with further implications for mathematics as a discipline. As I already said, if somebody comes to share your land or to tell you how many taxes you owe to the government, this person has to carry a certain amount of trustworthiness, of authority, of professional expertise. So the idea of their training and your perception of their authority has to be grounded, has to be real. Mathematicians were the instrument of justice in the ancient world. If mathematicians were these highly trained professionals that had to go through the land and measure and decide how many taxes or what inheritance everybody has, they needed to be taught. What are our ancient textbooks? In Egyptian mathematics, we have papyrus. Now, unfortunately, papyrus is not going to be very durable as a material, and therefore we have very, very few pieces of surviving papyri. This is basically ancient paper, and Egypt is, of course, situated in the middle of a desert, so this is something that disintegrates fairly quickly. The two largest papyri we have are the Rind mathematical papyrus that is named after Rind, who purchased it in 1858 in Egypt. It's also called the Ahmes papyrus after the scribe who last copied it. So clearly what we might have what we almost certainly have is not the original, but rather a copy of it. The origin of it has been established to be 1650 before Christ, so minus 1650, and everybody agrees that it was written much earlier. This is sort of not just a clean copy, this is a copy of the textbook that has already been used and proofread and is not in its first edition. Notice the actual size of it. It is 16 feet tall and 13 inches wide. It is as wide as your average textbook is tall. It is a very skinny but very long piece of papyrus. The other papyrus, the Moscow mathematical papyrus, purchased by Galeshnikov in 1892 or 93, is dated back about the same time and is 15 feet long, so approximately the same length, but 3 inches wide. That thing is really skinny, long piece of papyrus. These are our main sources of Egyptian mathematics. Each one of them is as you can see here, is a list of mathematical problems and their solutions. What is fascinating is that these problems are extremely fake. They are very similar in a sense to the problems that appear in current mathematical textbooks that we often make fun of for their sort of pseudo application nature. And these texts are the exact same way. There was no need for this mathematics to pretend to be applicable. These textbooks were textbooks to be used to teach these very highly specialized mathematicians that will then go out and divide the land. Right now, what we have is, in most mathematical classes, is we start with an abstract result or a principle, and then we go through examples to illustrate such principle. Ancient textbooks work the other way around. Practical information was communicated via examples to solve specific problems. But the ancient scribes did not bother making them any more applicable to real life than the current textbooks are. The society at the time didn't need mathematicians to only get the right answer. They also needed to be viewed as proper experts. And to be viewed as proper experts, you really needed this kind of technical education to support your authority. The actual numeral system in itself is really quite beautiful. So it is an improvement on the tally mark system. It combines the tally mark system as a concept of additive number system, but now instead of, for example, writing 10 tally marks for 10 things, we have a new symbol for that. Instead of writing 100 tally marks, we have a new symbol for that. So the symbols range from 1 to 1 million, where this is argued to be either a frog or a bird, and this is essentially, says an astonished person here, often considered to be a pharaoh, a million. This system is again additive, so simply writing the numbers together, you will produce the corresponding numbers. So for example, writing 3 pointing fingers will be 3 of the value that each finger represents, so 30,000. So this is something that is fairly easy to read. But let's think then, again, write down your thoughts on a Padlet of what does that mean in terms of advantages and disadvantages of this system? How does the arithmetic work in this system? Is it something that is easy to be taught, or are there any difficulties within it? Egyptian mathematics really rose to its purpose in a variety of ways. This is the earliest fully developed base 10 system. You noticed on the previous slide that everything was base 10. Every symbol corresponded to the power of 10. The Egyptians could add, subtract, multiply, and divide using a binary system, which is kind of amazing. And they could operate with unit fractions. In fact, they only operated with unit fractions. Unit fractions were, to them, the sort of molecular level mathematics. They would break up any fraction into unit fractions, so into fractions of the form 1 over something, and then would operate on those. They had extensive tables to show how those operations would work. They also did some more abstract mathematics. They approximated pi to within less than 1% with these seemingly primitive tools. They approximated areas of circles. They knew formulas for pyramid volume. That shouldn't surprise many of us. They also knew Pythagorean triples that are necessary in construction of their pyramids and in construction of right-angled triangles. Moving on to Babylonian mathematics, this is where we are extremely lucky that Babylonians wrote their mathematics, or anything in fact, on clay tablets. So they used a little stick tool that could make notches, as you can see, of the different shapes, but mostly of this triangular shape and just of a tally mark shape. And this was essentially their entire alphabet. However, because clay preserves extremely well in the dry conditions of a desert, we have literally uncovered thousands of these tablets in various shapes and forms. So some of them are kind of like drafts and explorations probably, and some of them are tables of known values. So these are, for example, 2 tables of the various Pythagoras triples, and some of them once again have this exact same content as the Egyptian papyri, where they have problem, solution, to train those mathematicians to be able to work as justice system out in the field. The main highlights of the Babylonian mathematics include the earliest known writing system. Because we have such good preservation of it, we also were able to follow some of the developments through that. They needed to describe large numbers because they were very interested in the lunar calendar that they developed to an extreme degree, in order to be able to track things like the flooding of the Nile and a variety of other things. They started with an abacus early on. They actually had a character for 0, which is an abstract concept not developed by many ancient cultures. They could do all of the arithmetic operations that are necessary, including square roots and cube roots to be used in geometric exercises. They developed not general methods, but rather, again, through example, various methods for solving linear, quadratic, and even some cubic equations, which is just astonishing. They were able to calculate a variety of areas. They were able to approximate pi with high accuracy, and were very aware of Pythagorean triples that have the name of the Pythagoras that came centuries after the Babylonian mathematics already discovered the importance of these numbers. The numeration system consists of only 2 symbols, 1 symbol for 1 and 1 symbol for 10, again etched into the wet clay with a stick, with this as a shape on the end, on one end, and this as a shape on another end, or a stick that was sort of angled to make either one of those marks. But the system is actually base 20. As I already mentioned, they needed large numbers to represent, to be representable within their system in order to track the lunar cycle that obviously operates on a fairly large cycle throughout the years. The system is again additive, but it's also a first place value system. The value of the symbol depends on the place in which that symbol appears. This is similar to our system. If I write 257, this 2 represents hundreds. So this 2 is in its value very different from, let's say, 2 that I position on the very end that only represents units. The symbol is the same, but its value is very different. The 60 we actually have inherited in many of the everyday things. For example, many of you probably only have digital clocks, but if you have the old school type clock, you would notice that 60 is still the number of seconds, the number of minutes that we use, and this comes directly from the Babylonians. From them, we also have the 360 degrees in a circle. Think about this. Why would there be 360 degrees? Why 360 and not some other number? Well, you can say 360 is nice because it's divisible by many things. So if I want to think about half a circle or quarter of the circle, 360 will provide nice numbers to be divided into. And so, for example, a quarter of the circle would be 90, which is still a nice round number. But the real answer to that lies in something else as well. 360 is a number close to the number of days in a year. 365, right? It's a number that they needed for their calendars, yet a number that has many factors. 2 things played into that, and this is still something that we use to these days. Once again, we can really start digging deeper about thinking what this system was good for when we think of its advantages and disadvantages. So go on Padlet and write down some, or read through and write down some advantages, disadvantages of this system as compared to ours, or as compared to the Egyptian one, or as compared to the tally system? What is good about this system and how does that affect its arithmetic? Here I give you just a quick outline of the Egyptian and Babylonian numerals, but please go view the student presentations on these two numeration systems and their arithmetic to really understand how the numbers and the system itself actually plays out in practice.